All right, Chemistry 111. This is Chapter 10, Chemical Bonding 2. We're going to look at molecular geometry and hybridization of atomic orbitals. So tonight we're going to focus largely on molecular geometry. And so in Chapter 9, we spent a lot of time looking at Lewis structures, right? We spent a lot of time looking at Lewis dot symbols and talking about valence electrons and then putting the Lewis dot symbols together to make good Lewis structures. Now, what if we had a formula like BeH2, that's beryllium hydride. And we actually looked at the Lewis structure of beryllium hydride during or in chapter 9. And we said that beryllium has 2 valence electrons plus hydrogen has 1 valence electron. There's 2 hydrogens. So that gives me a total of 4 valence electrons that I would need in that Lewis structure. When it comes time to draw the Lewis structure, I start with my beryllium. It's going to have 2 bonds. We went over the fact that beryllium is an exception to the octet rule, and I explained why in chapter 9. But when we draw the 2 bonds to the 2 hydrogen atoms like this, usually you'll find that chemists draw them in a straight line the way that I have here. Why wouldn't a chemist draw this bond, pointing up like this? Okay, why wouldn't I do that in my Lewis structure? Well, I'll make it very simple for you. Okay, the reason why a chemist would not draw it like this, where we have this 90-degree bond angle between the 2 beryllium hydrogen bonds, is that you know that each one of these bonds has 2 electrons in it, right? This bond has 2 electrons and this bond has 2 electrons. Well, electrons are negative. What do we know about like charges? Do they attract one another or do they repel one another? They repel one another. And so the name of the game is this: quit crowding me, bro. They want to get as far away from each other as possible. And so this is not the furthest I can get those groups of electrons away from one another, is it? If I erase this and I put them in that linear arrangement like this, where the 2 bonds are 180 degrees apart, then each pair of electrons is as far away from the other pair of electrons as is possible. And that is why when we have beryllium hydride, it adopts this shape, and we call this shape a linear arrangement, or we say the molecular geometry is linear because this is a molecule and its shape is linear. So the whole idea about electrons repelling one another, where I said, quit crowding me, bro, well, the proper term for that is Vesper. Okay, so tonight we're going to talk a lot about Vesper theory. What is Vesper? It's valence shell electron pair repulsion. Think about that. Valence shell electrons, right? These are the electrons that we need to make Lewis structures, to make our bonds, to make our lone pairs in Lewis structures that we looked at in chapter 9. And what are those lone pairs going to do? They're going to repel each other. What does that mean? That means they're going to get as far away from each other as is possible, right? Just like in our beryllium hydride molecule. If I have a central atom that has 2 atoms flanking it like this, and keep in mind there's no lone pairs on the beryllium, what are those 2 bonds going to do? They're going to move as far away from each other as possible. They're going to adopt this 180-degree arrangement. And I say that my molecular geometry is linear. It's perfectly straight. It's 180 degrees. Now, again, we call this class an AB2. It's 2 atoms bonded to the central atom, and there's no lone pairs. Now, before we move on, I want to cover one more concept before we get to the next slide. You're going to hear me say molecular geometry a lot this evening, and you're also going to hear me say arrangement of electron pairs, which Mr. Dion likes to call electron geometry. So I'll oftentimes call that electron geometry, and I'll call this molecular geometry. The difference between molecular geometry and electron geometry is this. Molecular geometry considers only bonds, okay? Only bonds, whether they're single bonds, double bonds, or triple bonds. It only considers bonds, molecular geometry. Electron geometry considers bonds and lone pairs. Okay, so we're going to look at Lewis structures wherein we have lone pairs. And so electron geometry is going to consider those lone pairs. Now, we don't have to worry about any lone pairs in our beryllium hydride because there are no lone pairs anywhere in the molecule. Okay, give me a thumbs up if you just follow me on the idea of the Lewis structure for beryllium hydride is as shown here. the two bonds are going to get as far away from each other as possible. They're going to adopt that 180-degree bond angle. I say the molecular geometry, which considers only the bonds, is linear, right? Because the bond angle is 180 degrees. And the arrangement of my electron pairs, which in this case, the only type of electron pairs we have here are bonds in the beryllium hydride molecule, is also going to be linear. And you're going to see several examples of Vesper models where the electron geometry is going to match the molecular geometry. But later on, we're going to look at a lot more examples where the electron geometry and the molecular geometry will not match one another. All right, let's move on from there. So here's a model of beryllium chloride, right? So we've already looked at beryllium hydride. If you look at beryllium chloride, it's the exact same thing that we just looked at, right? Beryllium is the central atom. It is bonded to two chlorines. There are lone pairs in the Lewis structure. However, the lone pairs are on the chlorines, right? On my central atom, I have no lone pairs. I have two bonds and no lone pairs. Therefore, my bond angle is going to be 180 degrees, like that. It's going to be completely linear. If I just turn off the slide here just for a second, so if I go back to here, I'll just give this the old college try here. My camera oftentimes will flip off. Yeah, here we go. So this is a linear model that I made. It's not that exciting. You know, if you look at it, you have the central atom in the middle, and then it's bonded to two other atoms. Now, I know that there's holes in my central atom, but this is all I had in my model kit. Normally, you wouldn't think of there being other, room for bonds or lone pairs in your linear model, but you can see that the bond angle is 180 degrees in a linear molecule. Well, what if I had three bonds around a central atom and no lone pair? How would those three bonds get as far away from each other as possible? Right? They would adopt a triangle. They would end up in a triangular shape like this, right? So here I have an atom with three bonds and no lone pairs. What's this molecular geometry called? Well, let's take a look. When I have three atoms around my central atom, so three bonds, or what I call sometimes three regions of electron density, I have a trigonal planar arrangement of electron pairs, and I have a trigonal planar molecular geometry. An example of this would be something like boron trifluoride. Okay, let's say you had BF3, and I believe that we looked at the Lewis structure of BF3 in the last chapter. So if we have boron trifluoride, I have three bonds to my boron, right? Boron is one of those elements that is an exception to the octet rule. Boron is element number 5 in the periodic table. Its valence electron configuration is 2s2, 2p1. It can only form three bonds. So here we go. And those three bonds are going to spread out from each other as far as possible. So the bond angles in my boron trifluoride are going to be 120 degrees, right? If you split a circle, if you take a circle and you divide it exactly in three, the bond angle is going to be, right? This bond angle would be 120 degrees. They would all be 120 degrees, right? You take 360, you divide it by 3, what do you get? 120. Okay, so my bond angle is 120 degrees. And since I have no lone pairs, right? I'm still talking about no lone pairs anywhere. My electron geometry, or my arrangement of electron pairs, is the same as my molecular geometry, which is trigonal planar. So now we've covered two molecular geometries. Central atom with two atoms, linear. Central atom with three atoms and no lone pairs, of course, trigonal planar. Well, I have a question for you. If I have four atoms attached to a central atom, how are they going to get as far away from each other as possible? Right? If I have four atoms, how are they going to get as far away from each other as possible? Or if I had four bonds, right? What is that? Now, if we were live, if we were, at a lecture hall, if we weren't in the middle of a global pandemic, I would ask you that. And a lot of times my students will say, well, they're going to end up in a cross shape like this, like a plus sign. They're going to have 90-degree angles. They're going to occupy the four quadrants of a circle, if you will, but that's not true. Okay, that is simply not true. If you have four atoms bound to a central atom, the furthest that they can all get away from each other is to adopt this geometry here. This shape is called a tetrahedron. Here I have what represents maybe a carbon in the middle, and then I have 4 hydrogens bound to it like that. So this would be a molecular model of methane, which is the simplest organic molecule possible, or the simplest possible hydrocarbon. Anyhow, all of the bond angles in this molecule, this one, this one, this one, this, they're all the same. They are all 109.5 degrees. Now, if you've never seen the tetrahedron before in maybe a math class or something, or maybe a geometry class, you might not have heard of that bond angle, but in fact, that is the furthest that atoms can get away from each other when they have one central atom and 4 atoms bound to that central atom. So I'm going to have to skip the next slide just in the interest of, I went right to the tetrahedron, but whatever. All right. This next slide was just showing the structure of boron trifluoride, right, where you have the boron and the 3 fluorines like this, okay, and the bond angle is 120. Anyhow, back to my tetrahedron. Here's my tetrahedron right here. Now again, since we have one central atom and 4 atoms bound to it, no lone pairs, right? 4 atoms bonded to the central atom. No lone pairs. We're going to get to lone pairs later on. That means my electron geometry and my molecular geometry will both be tetrahedral. All of the bond angles will be 109.5. So as I told you, methane is a good example of that. So the way that we represent the methane structure, if I was to ask you to just draw a Lewis structure of methane, right, and you said, well, carbon's in group 4A, it's got 4 valence electrons, hydrogen has 1 valence electron, there's 4 hydrogens, there we go, I have 8 valence electrons. Look, if you drew this for a Lewis structure, if you just said, I have a carbon and then it's bound to 4 hydrogens, there is nothing wrong with this Lewis structure. If I just asked you for a Lewis structure, I would give that 100%. The limitation of the Lewis structure is that it doesn't tell us anything about the shape of the molecule, does it? Because if you were to just ask somebody on the street, what's the shape of this? They'd say, well, all of these bond angles look like they're 90 degrees to me. But we know that that's not true. Because when we have that central carbon atom bound to 4 atoms around it, they're going to try to get as far away from each other as possible. So I'm going to have my carbon like this. I'm going to have 1, 2, 3, 4 hydrogens like this. All of the bond angles, every single one of them is 109.5 degrees, right? This one is 109.5 degrees. They're all 109.5 degrees. One more thing I want to address here is that since we're now getting into molecules that have a 3-dimensional shape that are not planar, right? Go back to our table. Linear molecules, you don't have to think about 3 dimensions, right? It all exists in, one straight line. Trigonal planar, that's flat. Well, the tetrahedron is 3-dimensional. So now we have to find a way to represent that on paper. And we use what are called wedges and dashes to show that. So this is called a dash. And what that means is that the bond is going back, okay, back into the page or back into the screen, if you will. This is what we call a wedge, okay? And this means is that, or what this means is that the bond is coming toward, or is pointing towards you, okay? It's coming towards you, okay? So again, dash means it's going back, wedge means it's coming towards you, which would mean that these two, since they're just drawn as lines, that would mean that those are both on the plane of the screen that you're looking at. So what have we covered so far? We've covered the linear molecular geometry, we've covered the trigonal planar molecular geometry, and we've covered the tetrahedral molecular geometry. Well, let's move on from there, and let's talk about what would happen if you had a central atom and 5 atoms surrounding it. No lone pairs, but a central atom with 5 atoms surrounding it. This is where, in my mind, it starts to get a little more complicated if you've never studied chemistry before. These ones, the next two, or this one I would say might not be as intuitive. The shape that you end up with is called a trigonal bipyramid, or we say it's trigonal bipyramidal. Again, since we have no lone pairs, the electron geometry and the molecular geometry are identical, and we end up with what's called a trigonal bipyramid. Now, an example of a trigonal bipyramid would be phosphorus pentachloride, right? What's phosphorus pentachloride? It's PCl5. If I was to ask you to draw a Lewis structure of PCl5 and you said, okay, I've got my phosphorus here, I've got a chlorine here, 1, 2, 3, 4, 5 chlorines. I'm going to fill up the octets of all of the chlorines like this. If you drew that and said, there's my Lewis structure, Mr. Dion, read it and weep. I would say, that's beautiful. There's nothing wrong with that Lewis structure at all. I would give that 100%. However, it doesn't show the molecular geometry. It doesn't show the shape of the molecule, does it? When we have the trigonal bipyramid, the way that we represent it is we have our central atom, which in this case is our phosphorus. We're going to have one chlorine pointing straight up, another chlorine pointing straight down, and then we have 3 chlorines in the middle, all splitting up a circle. So it's kind of like they're trigonal planar, like in the middle. So we have a chlorine here, another chlorine here going back on this dash, another chlorine coming out on this wedge. Now, if you're the kind of person that struggles with viewing things in 2 dimensions on a screen or on a piece of paper and then imagining them in 3 dimensions, this is where handheld models can come in really handy. Let me show you a molecular model of the trigonal bipyramid or the trigonal bipyramidal molecular geometry. So here's my model like this, okay? You can see how it's linear, it's linear between these 2 atoms here, right? If you look down that axis, right, you see that those 2 atoms are perfectly in line, right? But then around the center, we have 1, 2, 3 atoms in like a trigonal planar arrangement. So the bond, there's a couple of different bond angles in here, right? The bond angle between the top atom and the bottom one, like this, we call these the axial positions. This bond angle is 180 degrees, right? The bond angle between the axial and what we call the atoms in the middle, we call these equatorial. That bond angle is 90 degrees. And then the bond angle between the 3 in the middle is 120 degrees for each one of them. Okay, if you're struggling with that, let's take a look at it on the screen. So just give me a second and I'll show you what I mean. All right, here we go. So again, we have these 2 atoms right here, which are 180 degrees apart. You have a 90-degree angle right between the axial position and the equatorial position. And then you have a 120-degree angle between all the equatorial positions. So I'm going to color code these here. So these 3 positions, we call these the equatorial positions. So I'll highlight that in yellow. And if I highlight these 2, I'll highlight these 2 in green. We call these the axial position. Okay, so axial and equatorial position. Give me a thumbs up if you follow me up to this point. We've got linear, we've got trigonal planar, we've got the tetrahedron, we've got the trigonal bipyramidal. Well, I got some good news for you. We've only got one more molecular geometry where we have one central atom and no lone pairs. And so if we have a central atom that is attached to a total of 6 atoms, then we get what's called the octahedron shape, or the octahedral electron geometry, or the octahedral molecular geometry. Either way, it's the same thing because we've got no lone pairs on the central atom. Now, we actually looked at an example in Chapter 9 of an atom that can expand its octet to accommodate 6 bonds. And the example that we looked at in Chapter 9 was sulfur hexafluoride, Sf6. Again, and I know I'm repeating myself a little bit here, but if I asked you to draw Sf6 and you just drew, a sulfur with 6 bonds to fluorine, you know that fluorine only ever has 1 bond and 3 lone pairs. So you can, knock out this Lewis structure pretty quickly. I would be, very satisfied with a Lewis structure that looks like that. That's perfect. There's nothing wrong with that. However, it doesn't show us the shape of the molecule, does it? So what we have to do is we're going to have to put our sulfur in the middle like this, and we're going to have our fluorines all spread out evenly since we have 6 of them. Okay, we get this octahedral shape where it's almost square, like a square in the middle, and then you have 1 on the top and 1 on the bottom. But if you examine the octahedron carefully, you see that every single bond angle in here, okay, all of these bond angles like this and this and this, and right, those are all 90-degree bond angles. Okay, the only thing that's not a 90 degree would technically be this, which is a 180. Okay, so let's take a look at the model of the octahedron. And let me go back here. So here is my octahedral model right here. There it is. So you see you have the central atom. It's bound to 4 atoms in the middle. And then it has 1, 2 like this. But it wouldn't matter where I grabbed it. It's going to look the exact same. It wouldn't matter which atom I pick. It's always going to look the exact same because everything is spread out evenly. Every bond angle, this one, this one, this one, this one, this one, they're all 90 degrees. And that is my octahedron. All right. Now we've covered all of the molecular geometries where we have a central atom with bonds and no lone pairs. You need to be aware of these, right? You need to know the linear shape, the trigonal planar shape. You need to know, or molecular geometry. You need to know the tetrahedron, right? You've got to know the trigonal bipyramid, and you've got to know the octahedron. So you have to know all of these molecular geometries: linear, trigonal planar, tetrahedral, trigonal pyramidal, and you also have to know all of the bond angles in all of these, right? So you see how chemistry is a story that comes together, right? We started out just by drawing, Lewis structures for these type of molecules, and after we learned how to draw Lewis structures using Vesper theory, valence shell electron pair repulsion theory, we're able to determine the shape of a molecule, which is pretty neat when you think about it. Well, I want to stop for a second, and I want to take a look at that tetrahedron again. Let me go back to my camera, and there's something I want to show you about the tetrahedron. Okay, if we were to take the tetrahedron, so here's my lowly tetrahedron, like this, and just bear with me a second, I have to go down here to my model kit. If we were to remove one of those atoms from my tetrahedron, so let's say I pulled this one off, okay, and I replaced it with a lone pair. That's what this lobe represents. It represents a lone pair. Now we're getting into something a little more interesting because now my electron geometry and my molecular geometry are different, right? Remember I told you that molecular geometry considers bonds, 1, 2, 3, and lone pairs. So the electron geometry of this molecule that you see here is tetrahedral. However, the molecular geometry only considers the bonds. You see that it looks like a triangle like that? It's trigonal, but it's not planar, is it? Right? If you see it on my hand, it is not flat. So we call this a trigonal pyramid or trigonal pyramidal. Again, my electron geometry is tetrahedral, but my molecular geometry is trigonal pyramidal. All right. What if I removed another bond? So I just ripped off another one, and I put on another lone pair like this. So I'm going to look over at my chat. Could anybody tell me this molecule that I'm holding in my 2 fingers here, what is the electron geometry of this model that I'm holding up? The electron geometry, or the arrangement of electron pairs. Exactly. Thanks, Anthony. It's tetrahedral, right? Because electron geometry considers bonds and lone pairs. I have 1, 2 bonds, 2 lone pairs. That's 4. That's a tetrahedral electron geometry. However, my molecular geometry only considers the bonds, and that is called bent. You see how we have a bend in it right here. And this is actually a model of water, right? Water has a central oxygen with 2 bonds and 2 lone pairs. So you see how we went from the tetrahedron to the trigonal pyramid, or the trigonal pyramidal, to the bent molecular geometry by doing what? By replacing bonds with lone pairs. So let's take a looky here. And that's what's being represented on this slide. If you take a molecule like methane, this is CH4. We have the central carbon, 4 hydrogens surrounding it, no lone pairs on the central atom. We have a tetrahedron. Every bond angle is 109.5. What happens when we have a molecule like ammonia, Nh3? Well, you know that the Lewis structure of ammonia has 3 bonds to the hydrogens, but a lone pair. So the lone pair of electrons is in this orbital right here. Now, the thing is that lone pairs, these electrons in this bond are shared, right? Shared electrons, whereas the electrons in here are unshared, right? These are lone pairs, so unshared electrons. What's the consequence of these electrons being unshared? Is what they're going to do is they're going to push these bonds down a little bit more, closer together, and it closes the bond angle here, or it lessens the bond angle, which decreases the bond angle down to about 107.3. What if I had a water molecule, H2O, right? If you just drew a Lewis structure like this, technically there's nothing wrong with this, but it doesn't show the molecular geometry, does it? The molecular geometry of water is bent, right? You see how it's bent right here? You see how this is trigonal pyramidal, right? Because we have a lone pair here and a lone pair here. What's the consequence of those two lone pairs? They're going to push these bonds even closer together, right? Because these are both unshared electrons. They're not tied up in any way, and that decreases the bond angle even more. So what's the take-home message as we go from the tetrahedral methane to the trigonal pyramidal ammonia to the bent water molecule? Is that we see that the lone pair repulsion, right? If the more lone pairs we have, the repulsion is greater than if we have just a lone pair versus a bonding pair. And then if we have bonding pairs, right, shared electrons with each other, then their repulsion is going to be the less. So the take-home message, another way of saying this, is that the more lone pairs you have, the more they're going to push the other bonds or squeeze them together, if you will. If you want me to show you in kind of an animation of what's going on, and maybe I don't need to do this, but I can't help myself. I'll show you very quickly. Look what happens in the water molecule, right? The way the model is right now, you know, the way that I'm holding it in my hand, it looks like the bond angle between these, right? It looks like the bond angle here is perfectly 109.5. But what happens is the lone pairs here, they push these two atoms together. Okay, they repel them down like that, and it closes up that bond angle so it's closer to 104.3. Now, you don't have to memorize the bond angles of ammonia and the bond angle of, the bond angle of water. What I would like you to know is that when you have 3 bonds in a lone pair or 2 bonds in 2 lone pairs, that the bond angle is simply going to be less than 107 or 109.5 degrees. So what I'm trying to say, you guys, is that this bond angle, if you just said to me, you know what, Mr. Dion, I know it's less than 109.5 degrees. This angle, I know it's less than 109.5 degrees. That's good enough for me. If you want to memorize those numbers, 107.3, 109.5, there's nothing wrong with that either. All right, so there we go. Well, let's go back to that trigonal planar molecule for a second. Right, I even held up a trigonal planar molecule for you earlier this evening that I made. Well, what's going to be the consequence if we replace one of those bonds with a lone pair? So watch carefully, you guys. If you're like, I'm not sure what you mean by difference between molecular geometry and electron geometry, again, which is the same thing as arrangement of electron pairs. Look, if you have a central atom, A, with 3 atoms surrounding it, no lone pairs on that A atom, the electron geometry and the molecular geometry are going to be trigonal planar, right? But what if you replace one of those bonds with a lone pair? Then your molecular geometry, which considers only the bonds, right, would only consider this part like this, it's going to be bent, right? It's not going to be trigonal planar, okay? If you want me to show you in terms of a model, I can do that very quickly. Nope. There we go. If I take my trigonal planar molecule right here, all the bond angles are 120. If I replace this bond with a lone pair like that, what's it going to do? It's going to squeeze these two together a little bit. But now my molecular geometry only considers the bonds. That's bent. That's a bent molecular geometry like that. All right, give me a thumbs up if you follow me on the concept of going from the trigonal planar to the bent shape when we replace one of those bonds with a lone pair. Can you guys see my screen? I wasn't sure if I pressed share screen or not. Okay, good. All right. There we go. So bent. And an example of a bent molecule would be sulfur dioxide, SO2. Let's move on from there. What about that tetrahedron? I'm going to go over the tetrahedron a little quicker because I covered it on this slide right here. What happens if you replace with one of the bonds with a lone pair, or if you replace two of the bonds with two lone pairs, right? We covered this already. And I said if you have three atoms attached to your central atom and one lone pair, right? Like in the case of, an example of this would be ammonia, right? An example of AB4 would be methane. Then you still have a tetrahedral electron geometry, but the molecular geometry, again, only considers the bonds. And then you have something that's trigonal pyramidal. We covered that. We also covered bent, right? We said in H2O, right? In a water molecule, you have two bonds to hydrogen, but then you have two lone pairs, right? And so the molecular geometry considers only the bond here, the bonds. So the molecular geometry is bent, even though the overall arrangement of electron pairs or the electron geometry is tetrahedral. All right, I'm going to need to take a deep breath here because now we're getting into 5 electron groups. And this is the spiciest one of all, really. This is the one that has the most possibilities when we have the Trigonal Bipyramid. So I started out with the Trigonal Bipyramid with you. Okay, I had a model of a Trigonal Bipyramid. I still have it here. I'll have to use it in a second here. But what if we remove one of the atoms in the Trigonal Bipyramid? Well, you might remember that I told you that in a Trigonal Bipyramid, if you have A, B5, so if we have 1, 2, 3, 4, 5, like this. I told you that these are called the equatorial positions, equatorial, okay? And I told you that these two positions are called the axial positions. Okay, so when you start plucking atoms off of the Trigonal Bipyramid structure and replacing them with lone pairs, you do not touch the two axial atoms. You leave them in place, okay? They are not going to be moved. Like a tree planted by the waters, they shall not be moved. So you're going to have these two, and they're not going to move. So when you want to remove an atom, you remove one of the equatorial atoms. Say you want to remove one, well, you remove one, replace it with a lone pair. If you want to remove another one, you're taking that off, replace it with a lone pair, so on and so forth. Let me show you what happens is you take those equatorial atoms and you replace them by lone pairs. Set up again. And here is my, where is it? Okay, here is my Trigonal Bipyramid. Here are my equatorial atoms, not going to touch them. So here's my Trigonal Bipyramid. I'm going to pluck one off like this. And the shape or the molecular geometry for this, okay, my electron geometry is still Trigonal Bipyramidal, but my molecular geometry in the book, they call this a distorted tetrahedron. I've got an even better name for it. Okay, does anybody know what the other name is besides the distorted tetrahedron? Does this shape remind you of anything? Okay, I don't know if I can do a demo. Yeah, thanks, Anthony. It's the seesaw shape, right? If I could, use this as a fulcrum, right? It looks like a whoop, whoop, whoop. Right? This is really shitty animation, pardon my language. But anyhow, it's a seesaw. So you can call it a distorted tetrahedron. I suppose we should, because that's what the textbook calls it. But you can also call it a seesaw. Believe me, I'll know what you're talking about. The next one, if you rip off another atom and we replace it with another lone pair. So now we've got our two central atoms replaced by two lone pairs. Now we have what's called a T-shape. Okay, so we went from the Trigonal Bipyramidal to the distorted tetrahedron or the seesaw, same thing. Now we've got the T-shape. If I take off that last poor guy, that last poor lone pair, I don't even have another lone pair, do I? Son of a gun. Here, if I replace it with another lone pair, Can anybody tell me what that molecular geometry is? And it's not a trick. What would you call that molecular geometry? Thanks, Kristen. Absolutely. You'd call it linear, right? Your electron geometry is still trigonal bipyramidal, but your molecular geometry, jeepers, that only considers the bonds, and you're back to linear again. Now, if you're like, can I remove more? No, you're not going to remove any more. So there, we've just covered all of the changes that can be made to the trigonal bipyramidal molecular geometry as we replace bonds, and we replace them from the equatorial positions, and we replace them with lone pairs. We go from having one lone pair, we get the distorted tetrahedron, or the seesaw. Isn't that a hyphenated word? I don't know. Anyhow, from there, we go to the T-shaped. So we go to the T-shaped from there. Okay, when we have two lone pairs on the central atom, and then if we rip off the last one, we get the linear shape. So whew, there's a lot, right? When you have 5 electron groups, there's a lot going on. Okay, there's a lot of possibilities. Okay, let's go over this again. You can go from the trigonal bipyramidal to the distorted tetrahedron or the seesaw to the T-shape to the linear. And of course, that's going from 0 to 1 lone pair on the central atom to 2 lone pairs on the central atom to 3 lone pairs on the central atom. Capiche, caposh? All right. Right, if it was easy, anybody off the street could do it, right? Well, there's one more shape, isn't there, right? There's the octahedron. What happens if we remove a lone pair, or excuse me, a bond from the octahedral arrangement or molecular geometry, and we replace it with a lone pair? Well, again, I think the best way to show it is with a model. So let me get my model out here. And you find a couple of, got to be a couple of lone pairs kicking around here on the desk. All right, here's my octahedron. Okay, you can rip off any one of these bonds because all of the bond angles are identical. They're all 90 degrees. I'll pick this guy just for fun. If I rip that off and replace it with a lone pair, my electron geometry is still octahedral, isn't it? But now my molecular geometry, this is called square-based pyramidal. Oops, almost dropped it. Okay, or square pyramidal, or I call it square-based pyramidal. Here in the book, they call it square pyramidal. I'm just used to the way I learned it. But anyhow, square pyramidal, like that. And it kind of looks like, you know, one of the pyramids at Giza, maybe. You know, you could put the 4 sides on it here, and then paint it gold. You know, put a pharaoh in there. Okay, anyhow, what happens if we rip off another atom off of our central atom? We don't rip off one of the ones that are right next to the lone pair. We go the furthest away from it. And if we pull that one off and replace it with a lone pair, again, our electron geometry is still octahedral, but now this is called square planar. Okay, and all the bond angles are 90 degrees. What do you think? Pretty cool, huh? And that takes you to the end of the road. Those are all the molecular geometries and electron geometries that you have to know. So we went from the octahedron to the square pyramidal, or square-based pyramidal, to the square planar. All right. Let's go back here. Do you guys find the models helpful? If I show the models, or do you want me to just draw it? I think the models might help a little bit. I like to look at models in organic chemistry. I find they're really handy. Good. Okay, great. Thanks, Branson. As long as we're helping somebody, I think it's really beneficial to look. You know, a picture is worth 1,000 words. And then when you see a model, you know, it's in 3 dimensions. That helps me out quite a bit. So where did we go? We went from the octahedron to the square pyramidal, or the square-based pyramid, to the square planar, as we removed bonds to atoms and we replaced them with lone pairs. So if you're wondering, hey, is there a table that summarizes all this? Heck yeah. Now, it's a little fuzzy here, but this table is table 10.2 from your textbook, and you can take a gander at that. It's a great summary of all the molecular geometries that we just looked at. You can see it's kind of fuzzy here, but you go from bent to trigonal pyramidal, other bent to distorted tetrahedron, T-shaped, linear, square pyramidal, square planar. Anyhow, there you go. Like that. So again, I'm just repeating myself here like an old man, but you've got to be able to draw a Lewis structure for any molecule that I give you, and you've got to be able to determine not only its electron geometry, but its molecular geometry as well. So what's the strategy that we take? Okay, the first thing we do is we draw the Lewis structure for the molecule. Then we count the number of lone pairs in the central atom, the number of atoms bonded, and then we use Vesper theory to predict the geometry of the molecule. The best way to master this is to practice it, just like everything else in chemistry class. I just want to back up here. This is a table I took from an earlier General Chemistry 1 class that I taught a couple of years ago, and I thought this is a really good table that covers molecular geometries and electron geometry. So it says here molecular geometry at the top, but it can mean molecular geometry or electron geometry because you see here that we have two lone pairs, say, for example, in square planar. I just want to cover with you what reds means. Red, okay, so red, R-E-D, means region of electron density. And a red can be a bond, a single bond, it can be a double bond, it can be a triple bond, and it can be a lone pair. It can also be a radical, but we're not going to look at a hell of a lot of radicals. So a region of electron density, one single bond counts as a region of electron density. One double bond counts as a region of electron density. One triple bond counts. One lone pair counts. And so you can use this table while you're studying to help you familiarize yourself with molecular geometries. All right, let's say you have 4 regions of electron density. You've got 3 bonds and 1 lone pair. Well, you've got 4 regions of electron density. You've got 3 bonds, 1 lone pair. It's going to be trigonal pyramidal. All right, so this table can come in very handy, and I would recommend using this as a study guide, kind of as training wheels to help you, get used to drawing structures with their proper molecular geometries. Well, with all that in mind, let's take some time to try a couple of practice problems. This is example 10.1. There's not really enough space here for me to solve all of these, so I'm going to go over to a blank document here quickly, and we're going to take a look at the first one. So this is example 10.1, and we'll start with A, which is arsenic hydride. If you finished that one earlier, if you don't want to listen to me, you could try the next one, which is oxygen difluoride. All right, so if we take a look at arsenic hydride, well, where do we find arsenic in the periodic table? It's in group 5A. It comes below nitrogen, then phosphorus, then arsenic. So it has a total of 5 valence electrons, plus hydrogen has 1. There's 3 of those. So that means we have a total of 8 valence electrons. I'm going to put my arsenic in the middle. I'm going to surround it with 3 bonds to hydrogen, right? Because hydrogen always has 1 bond to it. Now I've used up a total of 1, 2, 3, 4, 5, 6 electrons. I have 8. My arsenic needs 2 more to complete its octet. And there we go. That's a perfectly good Lewis structure. So I have 3 regions of electron density, right? I have 3 bonds, single bonds, and 1 lone pair. So sorry, did I say 3 when I meant 4? My mistake. 4 regions of electron density. So how are those 4 regions of electron density going to get as far away from each other as possible? They're going to adopt a tetrahedral arrangement. I'll put the lone pair at the end of a line like this just to help show the overall shape of the molecule. I'm going to need to have 1 hydrogen in the back like this on a dash, 1 coming out on a wedge like this. Could anybody tell me what that molecular geometry is that I've drawn right here? Any takers? So this would be trigonal pyramidal. Trigonal pyramidal, right? I've got a central atom bound to 3 outer atoms and 1 lone pair. Okay, that means it's trigonal pyramidal. The bond angle here will be less than 109.5 degrees. Let's try the next one, OF2 or oxygen difluoride. For my oxygen, I have a total of 6 valence electrons. Fluorine has 7 times 2. That's 14 plus 6. That gives me a total of 20 valence electrons. Well, you know that fluorine always has 1 bond and 3 lone pairs, like this. No exceptions. So far, I've used up a total of 16 electrons, right? I've used up a total of 12 in the lone pairs, 4 in the 2 bonds. 12 plus 4 is 16. I have 4 electrons left over. I'll put them on the central atom. We're in the same situation here. We've got 4 regions of electron density, don't we? Look, we've got 2 bonds and 2 lone pairs on our central atom. And so those are going to adopt a tetrahedral molecular geometry, tetrahedral electron geometry as well. So I'm going to put my fluorines like this, like that, and then I'll have a lone pair going in the back like this, and then I'll have another lone pair coming out front like this. Now my molecular geometry is bent, right? And this bond angle here is going to be less than 109.5 degrees. And that's the kind of rationale that we want to take. Let's move all the way down to, let's move to I3 minus. So this one is D. We'll do a couple more. This is I3 minus 1. So iodine is a halogen. It has 7 valence electrons. We have 3 iodines. So that's 21 plus 1 from the minus 1 charge. That gives us a total of 22 valence electrons. We're going to have all of our iodines in a row like this. We'll put 3 lone pairs on the 2 terminal ones. Why? Because iodine is a halogen. The halogens usually have 1 bond and 3 lone pairs, but since this one has 2 bonds, it obviously doesn't have that arrangement. We can try that for the other 2. So far I've used up a total of 16 valence electrons. So that means I've got 6 more to go. Where am I going to put those last 6 electrons? Well, the iodine doesn't have a complete octet. If I put 1, 2, 3, 4, 5, 6 electrons around the central iodine, now it's got it's going to have a minus 1 charge because iodine has 7 valence electrons. Subtract 6 sticks and 2 dots, that gives you minus 1. Therefore, you're going to write a -1 charge on this iodine right here. So what's my electron geometry in this case? Can anybody tell me what my electron geometry would be? My central atom has 2 atoms bound to it and 3 lone pairs. What would my electron geometry be? We have 5 regions of electron density around it. That's right. It's going to be trigonal bipyramidal, right? Trigonal bipyramidal. But my molecular geometry is going to be linear. And so there's nothing wrong with the shape that I've drawn. I can just add some dashes and wedges in. If you want to draw it like this, right, where you put the 2 iodines up here, like that, and then you show I've got 1 lone pair going in the back. I've got another one coming out in front. I have 1 in the plane like this. I have a -1 charge like that. And there we go. Remember, the bond angle here is going to be 180 degrees. And so this is linear. There we go. Let's try one more and then we'll move on. So let's try E, which is a little more complicated. So this is 10.1 E. The molecule is C2H4. Well, remember that hydrogen only ever has 1 bond to it, like that. Okay, so there's not that many possibilities to arrange these atoms. Carbon has a total of 4 valence electrons. There's 2 carbons plus hydrogen has 1 valence electron. There's 4 of those. That gives me 8 plus 4, which gives me a total of 12 valence electrons. If I start with my carbon and I put 2 hydrogens on it like this, then I put another bond to like this, and I attach it to the other carbon and put these 2 hydrogens like this. So far, I've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 valence electrons. I have 2 more to go. If I put them on this carbon like this, that would give me a -1 charge on this carbon and a +1 charge on this carbon. Now remember that in Lewis structures, we try to avoid having formal charges if we can. We've got a +1 and a -1. So what if I took the 2 electrons that are on the carbon and I made a double bond like this? Now each carbon has a complete octet. Each hydrogen has a complete duet. My question to you is, if I just focus on this carbon right here, and they're both identical, could you tell me what the molecular geometry of that carbon is? Well, let's think about it in terms of reds, or regions of electron density. Remember that a region of electron density could be a single bond, it could be a double bond, it could be a triple bond, and it could be a lone pair. I've got 1 double bond and 2 single bonds. That means that this carbon has 3 regions of electron density, no lone pairs. Therefore, the molecular geometry at this carbon is trigonal planar. And the bond angle here is around 120 degrees. Right? The same thing applies to this carbon as well. It is also trigonal planar, and all of the bond angles in the molecule are about 120 degrees. So those are the kind of strategies we want to take when we're going from a Lewis structure in determining molecular geometry. So again, you're responsible for all the molecular geometries that we've looked at this evening. All right, well, let's move on from there, find out where I was. And let's talk about the consequence of what are called dipole moments, which can result in what are called polar molecules. Okay, now let's just say, for example, we had a molecule like HF, right? Hydrogen fluoride. This is just an example off the top of my head. Here we have our hydrogen, here we have our fluorine. If I asked you to draw a Lewis structure like that, there's HF. Now, HF has no molecular geometry because there's only 2 atoms, so it's not linear, right? In order to have molecular geometry, you've got to have at least 3 atoms in a row. Anyhow, there's no molecular geometry here. However, what do we know about HF? We know that fluorine is the most electronegative element in the periodic table. That means when I have a bond between hydrogen and fluorine, there's going to be an unequal sharing of electrons, aren't there? Right? Most of the electron density is going to be over towards the fluorine, and that's what's represented by the red in this electrostatic potential map. The red color is trying to show you that most of the negative charge is over on this side of the molecule, which is leaving this side mostly electron deficient, and so it's partially positive. That's what the deltas mean, right? Delta in chemistry means partially. Okay, we're not talking about a cation and an anion. We're talking about partial positive charge and partial negative charge. So that permanent partial separation of charge, we call that a dipole, and it results in what's called a dipole moment. That permanently, there's going to be more electron density on this side than on this side. Again, the consequence, and I'm repeating myself here, is that this side is more negative, or has more negative character, and this side is going to have more positive character. Now, in terms of dipole moments, how do we calculate a dipole moment? Dipole moment is represented by the symbol mu. Okay, so this is a Greek letter mu, or sorry, it's not mu, it's nu. Anyhow, nu. All right, so this is the symbol for dipole moment. Now, dipole moment is calculated as charge multiplied by distance between the charges. So here we have the charge, and I know it's just below. And here we have the distance. The charge is measured in coulombs. The distance is measured in meters. So when we get coulombs times meters, that gives us what's called the units of Debye. And when we have 3.36 times 10 to the negative 30 coulombs times meters, that's equal to 1 debye. So if you look up in a table for a list of dipole moments, you'll see them listed in debye. Now, I'm never going to ask you to calculate a dipole moment. Okay, I'll even write that in here. Will not ask you to calculate mu. Or no, that's mu. Shoot, I got to brush up on my Greek alphabet. I'm going to erase that. Mu is this, right? So this must be mu. Okay, anyhow, where was I? I'm not going to ask you to calculate it either way, so you don't have to stress about it a whole lot. All you need to know is this. The bigger, okay, the bigger the mu, the more polar the bond, or the greater separation of charge there will be. You could say a bigger dipole. Okay, there you go. So that's what a dipole moment is. Now, if you're like, well, what can a polar molecule do? Well, if you take a polar molecule and you just have a sample of polar molecules, if you look over here, you see that all the dipoles are just kind of arranged sort of randomly to some extent. Now, you see that they're not completely random, and if you're wondering, what do you mean by that? Well, if you look very carefully, you see how the pluses kind of line up with the negatives, right? There's a positive and a negative, right? They're going to there's another positive and a negative, right? They're going to, right? You see how the positive and the negatives, right? Opposites attract, my friends, okay? So that's what you see what's going on there, is that the dipoles do kind of line up to attract one another, and we're going to talk about that even more in chapter 11. However, if you apply a magnetic field or an electric field to a bunch of polar molecules, they will align themselves with the magnetic field, okay? So you see how we have the positive side over here, and all the negative sides are pointing towards the positive side, and then we have the negative side over here, and all the positives are lined up towards the negative. So that's what a polar molecule can do. Now, what you need to be able to do is to go from, and pay close attention, you need to be able to go from a Lewis structure to determining molecular geometry and electron geometry to determining what's called polarity. Okay, so you're going to have to analyze all of the polar bonds in a molecule and state whether the molecule is polar or not. So the first examples that we're going to look at are ammonia. This is NH3 here, and then this is nitrogen trifluoride, NF3. But before we take a look at those,